Hi, welcome to the lecture on binary neurons, otherwise called threshold logic neuron. So if you basically look at this video lecture, we will first initially go through an introduction and then I will give you an example as well. It would obviously be a solved example. So if you talk of the concept of classification, patterns are examples to be classified or represented as a vector of features. How are they encoded? They are basically encoded as integers or real numbers in a neural network. If you look into the concept of pattern classification, what is classification? Classification is basically taking an input and then dividing them into two or more classes based on the desired output. Whenever we talk of pattern classification, it is definitely a kind of supervised learning. We have already discussed the concept of supervised learning in my earlier video lecture. If you have any doubts, you can probably go back and look at that lecture, hear that lecture, and you will better understand what is supervised learning. So supervised learning is basically learning under the supervision of a teacher, which obviously gives better results than unsupervised learning. So this is what is called the separability in classification. Basically, there are three types here. The first one is called linear. So where I could probably draw a single line that could classify between the two classes. So I draw a single line that clearly demarcates or distincts between the two classes, shows some kind of distinction between the two classes. Then I call it to be linear. When I look at something called a non-linear separability in classification, I am not able to probably draw a single line to separate the two classes, but I could see some kind of a cluster where I have drawn something like an oval where it separates the two classes in a distinctive manner. The third category is called inseparable. Inseparable means both the classes are mixed together, even though by drawing a line, single line, or by drawing an oval or any kind of a shape, if I'm not able to separate these two classes, then that becomes what is called inseparable. So we have something called the linear separability problem. So if probably I have two different classes of patterns and they can be separated by a decision boundary, then I can represent this by means of a linear equation. The linear equation looks like this: b plus sigma I equals 1 to n xi wi equals 0. If any kind of a pattern basically satisfies this given equation, then I could say the classes or patterns are linearly separable. Then I could use a simple network then to correctly classify these two patterns. Then I have something called the decision boundary. The decision boundary is something like the W weight or the B bias and so on. And this decision boundary could be determined by some learning procedure, or I can probably find out this decision boundary by solving a linear equation. So there are two ways. You could adopt either of these two ways. Either you can probably have some kind of a learning procedure, or you could probably solve a linear equation and then probably find out the decision boundary. If, for example, this kind of a decision boundary does not exist, then obviously it means the classes or patterns are linearly inseparable. So whenever you come across a linearly inseparable problem, this problem cannot be solved by a simple network. So which means I could probably find out the solution for a linearly inseparable problem by looking at a more sophisticated architecture. So we have something called the binary neurons and the pattern dichotomizer. By looking at this diagram, I could say the input vectors represented by capital X is equal to 1, x1, x2. W0, W1 and W2 represents the weight vectors. Constant is +1, no doubt. So I give an input of +1, which is a constant. Similarly, I have something called W0 or W0, whatever you can call it. That is called the internal bias. And it produces some kind of an output called S equals S of Y. Yeah. This is how a binary neuron and a pattern dichotomizer works. It has a set of input vectors, it has a set of weight vectors, and there is something called a constant represented by +1 and an internal bias represented by weight W0, which produces S, an output. So if you look at this binary neuron and pattern dichotomizer, you should be able to understand that, for this to work, you need something called the activation function. That activation function is probably written with Y equals X transpose into W. W is the weights, W0, W1, W2. X could be, x1, x2 and +1. So I have X transpose into W. So I get something like x1 W1 plus x2 W2 plus W0 into +1. That is why it is written as W0. When I can say, a neuron discriminant function could be written as y of x equal to 0, which means if y is greater than 0, I can say s equal to 1, else s equal to 0. Simple. So when you look at this discriminant function, I could very well say, given a fixed set of weights, the neuron will fire +1 for the inputs x1, x2 that would yield a positive activation function, and the neuron will fire a 0 if the inputs probably will yield a negative activation. So what I could probably understand from this is the inputs are separated into two classes. It is a binary class problem. The inputs that satisfy this discriminant function will yield 0 activation. So if you look at the previous equation, the previous equation is rewritten as follows. x2 equals minus w1 by w2 into x1 minus w0 divided by w2. w0, w1 and w2 are the weights, x1 and x2 are the inputs. So based on this equation, we will solve a problem later in this lecture. So stay tuned till then. When you look at the discriminant function, The neuron discriminant function given in the previous equation rewritten basically represents a straight line in a two-dimensional pattern space. So this kind of a straight line basically slices the plane into two different halves. One half will represent certain kind of patterns that will cause the neuron to generate a positive inner product, and hence this will definitely fire +1. The other half would obviously on the pattern space will cause the neuron to generate a negative inner product and will fire a 0. Those are the two possibilities. It will either fire +1 or it will fire plus whatever 1 or 0, +1 or 0. So it is obviously a binary problem at the end of the day. So what we are going to see now is some examples for geometrical design. So we will go into that problem now. Now when we look at the geometrical design of an AND classifier, okay, so let us say the neuron activation can be written as y equals x transpose into w. What is x? X is the input. What is w? W is the weight. So let us assume we have two input vectors written as x1, x2. The corresponding weights are written as w1, w2. When I can model this diagram, I can say x1 and x2 are the inputs, w1 and w2 are the weights, and then I have an activation function, and w0 represents the bias. Let us consider for this problem, we assume the value of w0 to be equal to -1.5. Then I have the weights w1 and w2 to be 1. Now, when you compute the weighted average, the formula is y equals x transpose into w. The input vector is x1, x2. Then you transpose it. Then x transpose into w becomes x1 w1 plus x2 w2 plus w0. So when I can rewrite this equation, now x2 equals minus w1 by w2 into x1 minus w0 by w2. So when you rearrange all these kind of equations, since the perceptron is a linear model, so it should probably be similar to a line function. The line function can be written as y equals mx plus c, where m is the slope, c is the constant. The equation that I have got is x2 equals minus w1 by w2 into x1 minus w0 by w2. When I can match this equation with the line equation y equals mx plus c, then I can say m equals minus w1 by w2, which is called the slope. Then minus w0 by w2 can be matched to c. C is a constant. So what is c here? As per the line function, it is called the intercept. So the slope equals minus w1 by w2 and c equals minus w0 by w2. So this is how we have probably matched the line equation with whatever we have derived. So since the perceptron is linear, I am matching it to a line equation y equal to mx plus c. Okay, so now we go for solving this AND function using this discriminant. So what are the weights we have assumed? w0 is minus 1.5, w1 and w2 are 1. So what is the slope as per the earlier equation? minus W1 by W2, which will give you minus 1. The intercept is minus W0 by W2, which will give you 1.5. Now, when you can plot this on the graph, you get W0 equals minus 1.5 yields a neuron classifier that approximately partitions the pattern space. So let us assume the value of the threshold is minus 1.5. Now, when you look at the AND gate, you are very familiar with the output of the AND gate. To probably quickly tell you again how it will work, how the AND gate basically works. Yeah, when both the output is 1, when both inputs are 1, the output is 1, else the output is 0. So that is what we have done here. You can look at this video and very clearly solve it. Considering the first input 0, 0, I will tell for 1. Similarly, you can do for the others. Then you do a transpose and then multiply and get minus 1.5. So since y of x equal to 0, s is 0. Similarly, you get minus 0.5 and minus 0.5. So the output s equal to 0. So in the last one, so what you get when you compute, so you will get plus 0.5. Plus 0.5 is greater than 0, so s equal to 1. So does it satisfy? Yes, it satisfies the AND function, right? So this is how it works. So if you look at quickly the summary, the threshold logic neuron employs a single inner product based linear discriminant function. The hyperplane divides the space into two regions. So we say that the TLN dichotomizer is by using a hyperplane decision surveys. The position of the hyperplane is proportional to W0, and the classifier employs a linear discriminant function, and it is always called as what is called the linear machine. So this presentation has given an overview of the binary neuron and pattern dichotomizer, how it will work, and I have also shown you a working example using the AND function of how you can probably apply this binary neuron concept in the pattern dichotomizer and check the validity and so on. So stay tuned for more video lectures on neural networks. So this concludes the concept of binary neurons and pattern dichotomizer. Yeah, thank you.